Good afternoon. The slide is visible.
Yes.
So we were mainly discussing about the classification, and for that we discussed thoroughly this linear logistic regression after the linear regression. So the idea is that uh, what whatever we have discussed so far, our discussion is on the binary classification. So that means there is the two class, basically there is a two class there, and there is some uh, decision boundary on these this class. Now the question is that if there is a more than two class, or you can say the multi-class classification. So if we have a multiple class, we actually do a very interesting thing. We use the binary class and we repeat this. That what we are going to do in this particular, that is one versus all, or we can say one versus rest. That means you see that since this is a kind of classification, so let's say this is a cat, this is a dog, and this is a horse. Okay, so what we are going to do here, that we first classify this cat versus non-cat. Okay, so we can classify something like this. Okay, as whatever we see that h theta 1, so this is our hypothesis function 1, hypothesis 1 or hypothesis function 1. Okay, then what we're going to see that, okay, that we find that second classification, this is number 1. Second classification will do that horse versus no horse. Okay, so we what we'll do, we put a decision boundary something like that. So here, so this is our hypothesis 2. Okay, and thirdly, what we'll do that dog and no dog. So something like that, we are doing this kind of hypothesis function. So apart from this dog, and left hand side is non-dog. So exactly here. So this is our hypothesis 3. That is easily been done using our whatever we have discussed so far. And then we adjoin these 3 hypotheses. So training logistic regression, for each class, we predict the probability this on the new point x to make a prediction, pick a class and that maximize. What is maximization of this? So what actually we're going to do here, the ultimately when we adjoin these two, it essentially do this kind of thing. So this is going to be your multi-class or 3-class classification. Okay. So this is very easy to start, and we can go for more classes. If it is a 4-class, 5-class, or n number of classes, we can repeat this and we can get easily this multi-class classification. So this concludes our discussion on the simple, very simple classification. Okay, so that this classification techniques is very simple in that sense. And today, actually today's agenda is another classification process, and we see this is also a very simple, better to say the simpler than this logistic regression, and we'll see that how actually things are changing in this way. So I stop. Today we'll basically try to understand a very well-known classifier. I should say it's a much, you can say, older classifier. So, and it is another supervised learning classifier. It's called KNearest Neighbor classifier. Okay. So let's take a recap. So whatever we have discussed so far, and what is we are going to understand here. Okay. Now, so we are, first of all, we are doing a supervised learning system. Supervised learning problem. So what do you mean by supervised learning problem? It is very easy that we have some thing is given. Okay. Some points that is been given, and we have to find out any other point in between. Okay. So this set of examples, a set of examples are given, and it is called training sample. Now these training samples are labeled. That means it is not xi or corresponding yi has been given. So this is given in this way, since it is supervised setting. So labeled data. That is very important. Now we have to find a suitable hypothesis function h. Okay, and this hypothesis function, we say this h belongs to a hypothesis class, this h. Now what do you mean by this hypothesis class? So it is very easy to say that in a very simplistic form, what we have discussed, that hypothesis class is a type of, you say, classifier. I should not say classifier, or you can say detector. Okay. So this is a kind of, okay, it may be sometimes what we very much said, that it is not that every, for a given, no single hypothesis function works equally well for all data or data distribution. So this we said that this is no free lunch theorem. That's what we mean. There will be no single universal algorithm. Okay. So sometimes we may go for logistic regression. something going for neural net, something for SVM, and so on. Some decision tree and KNN, KNearest, whatever. Okay. Now, so this is a hypothesis function, is a type of function. Now, the thing is that so this is a kind of assumption. First, what kind of hypothesis function we're going to choose. And there is another assumption that let's say we choose a logistic regression. So, but we can say again that we can assume that our hypothesis function H is linear. Okay. So this is another assumption we can make. Okay. But the thing is that the things is not ended here. Now, even if we can say that this kind of example, so these are the data point is being given this process. Now there is what we can say, there is a, if even it's a single line, this is a multiple this kind of line possible. Okay. So if we have a multiple line, we have this H is a set of such hypothesis function. And what is our job? We have to find the best hypothesis function. H belongs to. That's what you have to find. So that is basically your learning. So to try to find the best out of this. Now here, something we can see here also that this is our hypothesis linear. If it is a non-linear, we can say this kind of, this may be a curve of this sort, or is a more complicated curve. It's a curve of lower degree of polynomial, and this is a curve for higher degree of polynomial. Understand? So this is the whole story that we are going to understand. Now here you can see how to find the hypothesis class. So that we can say we have make assumption. So some assumption is required. That is the thing. So example, this function is linear. This is one assumption. Let's say it is a linear or logistic regression, and the corresponding function is linear. So these are not our hypothesis function. These are the function which is non-linear, and this is the linear function. And what do we say? These are different function. And how we get the best function? We use a loss. We define a loss. What is loss? Loss is basically how we have defined that h theta xi, that is predicted, minus the corresponding yi. We take square of this, the squared loss, and we sum it up. I is equal to 1 to m, where m is equal to number of samples or training samples. And we normalize it with this term. Okay, this is the loss. And what we have to go to? We have to arg mean of this loss with corresponding this theta. What is theta? Theta is parameters for our hypothesis function. So that is where, so if we have to minimize the loss, we can get in this particular the best linear hypothesis. That is what we have done so far. So this is the what we are basically trying to understand. Now we trying to do another new hypothesis function or new way of doing this. Now let's say this is the so here idea is that these are the some labeled is there. Okay. So some sort of labels are there. Now the question is that now let's say given this you have given a new data point that is testing here it is. Now can you say that this particular data point is either belong is two class problem. One class is belong to cross and another class first class second class is so which class this particular thing belong to? Can I say it? Anybody? Hello.
Could you repeat the question?
So the question is that this particular point is given as the new data point. So given this setting, this point is belong to which class? This cross class or circle class?
The first class,
That means cross class. Why?
because it lies in that region. I mean, it's if this is a classification problem, it'll probably classify it as a member of the X class only, I think.
So anybody thinks differently?
So distance from the intrinsic point is nearer for that class one.
What points?
So something called intrinsic point.
What do you mean by intrinsic?
So average of all the points.
Is it called intrinsic?
I forgot the word. Means uh, the point which is the center point of the first class is uh, nearer to that.
Yes, that makes sense. So that you say that if we take a kind of cluster and this is another cluster, and if you say this is a center of cluster here and this is a center cluster here, this thing is nearer here than this. That's you want to say. So that is very much intuitive. Okay. But this only happened, or this is intuitive fine, but this only happened under some assumption. So what is the assumption? The assumption is that similar inputs have similar output levels. So similar in that sense. So what similarity? That means this is a kind of Euclidean distance, or some sort of, I should not say Euclidean, some sort of distance. Okay. So what is the rule? Classification rule. For a test input x, assign the most common label amongst its k most similar training. Now, what is the point here? That here in this particular example, you see that if you say that you take the three nearest neighbor, let's say this is 1, this is 2, and this is 3, and this particular point, the nearest member is this and this, and since all are crosses, so we can say this is belongs to crosses, because the nearest neighbors are belong to crosses. Okay, so I'll check another scenario that may be bit complicated scenario here. I just anyway. That let's say these points are here. Okay, and this point is somewhat here. Okay, now things is bit complicated. Complicated in that sense that ideally, if you see the nearest neighbor, if you consider the nearest neighbor, this is the nearest neighbor. Let's say 3 nearest neighbor, where k is equal to 3. That we check. Now here you can say that you have to use the majority voting. That 2 is 2x and 1 circle. So again, this point is belong to this class. So this is the way it has been defined. Okay. So the idea is as simple as this. Okay. So let's try to formalize it. So the formal the borderline incomprehensible definition of k nearest neighbor is basically that the test input is x, denote the set of k nearest neighbor. So how this k nearest neighbors is defined? Okay. So now you can see x. So k nearest neighbors is a, so what I'm trying to say, that k nearest neighbor means these nearest neighbors or these 3 points. Okay, this is the, we are now defining what do you mean by k nearest neighbor. If you say and if we point, okay, this is the point, the k nearest neighbor is basically defining in this way. This is k nearest neighbor, and for this, for so k, where k is equal to 3 nearest neighbor for the point plus, that we are defining. And now what we are going to define, this case neighbor is basically Sx. So all these points, these 3 crosses. How we are going to define Sx? So Sx is definitely belong to all the data points, whatever the data points are being given. So whatever. So total data points, what all the data points are basically given D. So Sx definitely from D. So all the given data points. So that such that the cardinality of Sx, definitely the cardinality, you see, the Sx cardinality is K, where for our region it is 3. That also is very easy to understand. Okay. Next, for all x and y, so that is, now what I'm trying to say, all other points x bar y, so y is this definitely is level. It is belongs to D, but not in Sx. So Sx. So what I'm trying to say, this point, this point, this point, these are all these points we are talking about, which are from the D, but not from Sx. तो इसका अंदर नहीं है, इसका बाहर का जो point. If this is so, distance of x bar. Now distance of x is now what? X is our plus this point. So distance for x or of this point x bar is always greater than is equal to maximum. So the furthest point, maximum bar y bar. So this is the just a pair of this thing. Maximum of this for distance x double bar. What does this mean? See, distance x bar greater than or equal to maximum. This x bar belongs to x. That is forget to write. That is distance of. So that means this, you just consider this point plus within this circle. That means within nearest neighbor. Those nearest neighbor, which is the furthest point for this plus. Okay, so that is the maximum distance. This x bar is maybe this x, or this x. But which x is the furthest than this plus? That is also less than is equal to the any other point outside this cluster or nearest neighbor set. That is very easy to understand. That if you can say, for example, this particular point is furthest point from this is the furthest distance. Okay. Now this distance also less than this. Okay. So that is, we say, that is where we define the our k nearest neighbor. But this k may be anything. Okay. Now if you have any doubt, anything, you can ask. Okay, it's clear. So that part we understand. So every data point or every point in D, but not in Sx, is at least as far away from X as the furthest point in Sx. That is exactly what we have discussed. We can then define the classifier H as a function returning the most common level of Sx. So definitely this, which is the in this way, which is the most common means, if you say in this example, you can see here, or you can say here also, you can in this example, that in this X, these two are blue circle and one is kind of the red blocks. So you can say 2x. So this become, this particular X belong to the blue circle. Since number is 2, that is 1. A binary classification example case equal to 3. The green point in the center is the test sample X. The labels of 3 neighbors is 2 into +1 and 1 into -1, resulting in the majority predicting +1. That means that the +1. So this is the blue circle. So this is the way our classifier works. Okay. Okay, it's a very easy, very easy to understand. Now, But here you can see that in this particular way of classification, this K-neighbors classification, what is very important that we can say that a particular given or query point or a testing point X, the distance is very important, because you see what some of your friends answer very correctly, that this particular point, if I say this and this, this and this point is basically close to this circle. But closeness, so what is mean by the closeness? Closeness is defined by the distance. So how it is? Distance from this. And this distance is a, now you know, this is for your understanding, this is a two-dimensional space. Okay. Now it may not be two-dimensional always. In most of the cases, this is a high dimensional space or higher dimensional space. Where d is equal to greater than 2. So in this even higher dimensional space, you have to find a proper distance measure. Here it is called very easy, that is a Euclidean distance kind of thing, and you can do that. Okay, so distance is a very important. So distance function is making a very crucial role here. So we have to define a distance properly. The K-nearest neighbor classifier fundamentally relies on distance metric, and that is very important. So fundamentally relies on a distance metric, and that is important. So better the metric reflects the level similarity. So now that it's closeness means what? The better the metric reflects the level similarity, the better the classification will be. Okay. So the most common choice in this case in the literature is called Minkowski distance. Minkowski distance. So this distance is basically measured in that x in a odd dimensional space minus another x z in another odd dimensional space. Okay. And so this module to the power p, and this r is equal to 1 to this d for this distance, and then this particular dimension, the number of data points basically, and this is going to 1 by p. Okay. Now you see, if p is equal to 2, now what is this? That x r minus z r is basically taking the square of this. Okay. And this is r is equal to 1 to d, and this is, so it is basically a Euclidean distance. यूक्लिडियन डिस्टेंस क्या होता है? This is the Euclidean distance. Okay. If I'm not very wrong, this is basically the way Euclidean distance is measured. Okay. So that is interest. And if p is equal to 1, it is called Manhattan distance. Oh, this is y1. Sorry, this is yx1, x2. This y1. Okay. So this is the distance function we generally use. Okay, so far we have seen that how actually this kind of k-nearest neighbor works in this way. Okay, so now the question is that now whatever we have discussed, that our simple understanding is basically are two-dimensional. So we are in a R space, so that we can understand it very. So the KNN classifier makes the assumption that the similar points share similar levels. That assumption we have understood very, that it is if the kind of those close to the cluster center, it will be that kind of. But in the high dimensional spaces, the question, this is a very interesting point that I'm trying to say. But in the high dimensional space, points that are drawn from a probability distribution, so high dimensional probability space, I'm saying, that tend to never close together. So this is a bit complicated to understand or visualize. But first of all, we try to understand that if we say our assumption of, let this kind of, when we are classifying something, this is, let's say, apple and non-apple. What is our normal thinking? If the number of feature is high, then we can get better classification. Because the number of features, if number of features, it will much more well represent the points. Unfortunately, this assumption or this intuition not always correct. And this thing is called the cards of dimensionality. If we have that very simplistic manner, we say that if the dimension of feature dimension is very high, it may not always be good for the classification. Okay. Now here we are trying to understand mathematically that how it is important, or why this so, and it depends on the dimensionality or effect of dimensionality, better to say, effect of dimensionality depends on type of class, type of hypothesis function, or hypothesis class, or you can say class. Okay, or better to say the assumption what we are making to choose a hypothesis class. Okay. Now the thing is that in for KNN kind of classifier, where the distance is important, where the similar points set at similar levels. Now you see that this high dimensional space, these points that are drawn from a probability distribution tend never to be very close together. So this we can illustrate with a very simple example. Now what we'll assume that we draw the points uniformly at random. So that you can see that we can say that in a particular space, maybe it is a high dimensional space, and we can take a point that are distributed in what? Uniformly random. Okay. So these are uniform. This is our assumption. We assume this. And we will investigate how much space K nearest neighbors of a test point inside a cube will take up. Now we take an example here. So you see here that we formally imagine a unit of cube. So this is 1, this is 1, and this is 1. So we take a bigger cube, that does bigger unit cube in this. Okay. This is let this is our data space where the data is distributed in uniformly random distribution or uniformly randomly. So all training data is sampled uniformly with this cube. Okay. And we are considering k is equal to 10. So k is equal to 10 is k 10 nearest neighbor. 10 nearest neighbor of such a test point. Now you can see that we imagine a cube in this, a smaller cube of one this distance, let's say L. Okay, this L is much lesser than 1. And what is this? This is a space where all the nearest neighbor of these points are belongs to. So L is the edge length of the smallest hypercube that contains all k nearest neighbor of a test point. So the ये test point जो है उसके all the nearest neighbor is basically we imagine within this cube. Okay. So what we can say that this L is a basically kind of a, this is a, for your understanding, it is we draw is a 3-dimensional way, but it is a LD dimensional. So that the area or the space within this L is L to the power D. Okay, this is space. And definitely, if it is a uniformly distributed points, you can say total number of points within this K. This is K neighbor, so K. And if total number of data points is N data point, it is K by N. It is most likely K by N. Okay. So now you can see if N is equal to 1000, how big this L is. Okay. Now we can get an idea that L, if LD is equal to K by 10 means what? K is 10 and N is 1000. Okay, and this then L is equal to 0.01 to the power d, 1 by d is okay. So k by n, correct me if we're wrong. So something like that. Okay. Now, if you think that let be the age of length of smallest hypercube that contains all k neighbors, and if you say n, now you see, now you increase the dimension. So d is the dimension. Now, if it is 2, then what is will be the L? So it is basically 1 by d. So root over, so this is 0.1. Okay, because k by n is basically 10 by 1000. Okay, so it's a 0.1. If it is 10 d-dimensional, it is a 2-dimensional first. Now it becomes 10, so it becomes 6.63. Now, but one thing you understand, this is that this particular big thing is 1 only. So it is a 1. This is basically training data is sampled uniformly. So this cube is basically a 1 cubic area. And now we are trying to find out what is L. If we go to the 100 dimension, okay, then it is 0.95. You see, our key is 1, it's 95. If it is 1000, it is 0.995. So what is exactly happening here? That if you go for a high dimensional space, the area or volume or whatever in the high dimension of the space of your the smaller thing, if we try to find out in this way, that okay, this is your total space, and when d is equal to smaller, this is your nearest neighbor. Now what happened, if you increase the dimensionality, what happened, it will keep on increasing. And when it is a very high dimensional 0.995, so you can understand that this is very, this is your only a nearest neighbor, only 10 points. And in this edge portion, very tiny portion, all 99, total 990 points remains. Okay, so this is very tiny space. Okay, if this is the dimension is very high. Now actually what happening, if you see that if this kind of thing happen, now you see that this is, let's say, your, and this is your, now let's say there is a one class here that is within your neighbor, with your neighboring cluster, and there is a here. Now you see here it is your cluster center, this is your query point, let's say it is a star. Now distance from this and distance from this is more or less same. Okay, so that is the major point, major problem is happening. If your dimension is very high, then you can say almost entire space is needed to find this 10 neighboring neighbors, because it's very problematic or very tough to visualize that if it's a very high dimensional space, the points are very much in a distance. That this breaks down the KNN assumption. So you can understand why we say that KN is not a good classifier for a high dimensional space. And that's why the cards of dimensionality is called, because KNN is not particularly closer and therefore more similar than any other data points in the training set. Why would the test points say at the level with those KNearest numbers if they are not actually similar? So that is the major problem of KNN when the dimension is extremely high.
Excuse me, sir.
Yes.
Sir, I had a slight doubt. Since we are studying this KNN, so KNN is a algorithm, right? So how is this machine learning exactly? I mean, how is it learning per se?
Learning means what? What is the assumption here? That assumption is similar points share similar levels. So the thing is that what is the learning? Learning is basically that we took this kind of points. So you know the data points and levels are there. Now if something is coming here, you can say learning is this. Since this is this cluster center, you know that what he said. If it is a closer to this, you know the cluster center, then it is belong to this cluster. If it is if something is coming here, let's say the star kind of thing. So now this is close to this cluster, so it is belong to. So learning is that knowing the cluster centers, knowing the distribution and these clusters. That's all. That is the. In any case, what is the learning of a logistic regression? What do you mean by learning? Your question is that what do you mean by learning here? What is learning? So what is the learning in logistic regression? Can you say?
So yes, sir. So I mean, if we are suppose trying to do a linear regression, so in that case we have some parameters and we can update those parameters as the according to
Yeah,
the
so
data provided.
it is the linear regression. It is mx plus c, and you have to know m and c. That is the learning. So that it we this m and c, that is as a we said the theta 0 theta 1, such that we can get a much more we can get a line or linear curve that is well approximated this given data samples. That is the linear regression. Okay, so here also you can say that this particular data points, you know this cluster center or something, that when that ultimate question is that if a query point is come, so which level it belongs to, that you can say by virtue of which this cluster center or closeness of this thing, it is the thing that this particular the distance measure you can understand that which distance it is, basically how it is distance. If you consider this k neighbor, no this k parameter is also a hyperparameter, so you could say the 3 nearest neighbor, that as for our example, you see that you take the distance of this parameter to all this, and you just take if number of particular this star this cross is high, then it is belongs to cross. So this is the kind of learning. These parameters are basically, you have to know the parameters, then you can. So it's a much more trivial form of learning. Logistic regression, linear regression, you have a lot of things we have to, but here is a much more simpler or trivial form of learning. Got your answer?
Okay, sir.
Okay. Okay, we'll stop here today, and then we'll see that how to solve this particular thing in case of KNN or high dimensional spaces. Okay, thank you.